Dear students, after studying this module, you shall be able to understand the position of proton attached to primary, secondary and tertiary carbons, understand the effect of hydrogen bonding on the position of OH proton, learn about exchangeable protons and D2 exchange, know the effect of electronegativity, shielding, inductive effect and anisotropy on the chemical shift of different functional groups. It is necessary to know about the chemical shift values for different type of protons because it helps us to determine the structure of various organic compounds. Now, the chemical shift, as has been told to you previously many times in the earlier modules, varies with the electronic environment. The proton attached to carbon, oxygen, nitrogen or sulfur appears at different positions due to the difference in electronegativity. The chemical shift values also depend on the type of carbon to which the hydrogen is attached. Now, say for example, protons attached to singly bonded, doubly bonded or triply bonded carbons appear at different positions. The anisotropy effect caused by the circulation of the pi electron also affects the chemical shift position of a particular proton. In addition, students, we also need to learn here about the coupling behavior of the concerned proton with other neighboring protons to assign the structure of a particular compound completely. Now, let us study the chemical shift values for various functional groups that we come across generally. First, we would like to take up alkanes. In alkanes, aliphatic and saturated hydrocarbons, that is, CH absorption occurs in the range of about 0.7 to 1.7 ppm. The hydrogens in a methyl group are the most shielded, followed by methylene and then methine protons. The methine protons, that is CH, have a larger chemical shift than those in methylene or methyl groups. The chemical shift value range for methyl protons is 0.7 to 1.3 ppm and for methylene protons is 1.2 to 1.3 ppm. And for methine hydrogens it is 1.4 to 1.7 ppm. In long hydrocarbon chains or in larger rings, methylene and methyl hydrogens may overlap in an unresolvable group. Signal due to the methyl protons are usually separated from other hydrogens, being found at lower chemical shift values, that is in higher field. However, even when methyl hydrogens appear within an unresolved cluster of peaks, the methyl peaks can be often recognized as strong singlets, doublets or triplets depending upon the number of hydrogens on the adjacent carbon atom. Now, in the hydrocarbon chains, hydrogens on the adjacent carbon generally couple with each other following the n+1 rule for spin-spin splitting. The coupling constant values for this will be approximately 7 to 8 Hertz. Now students, we shall go to functional group of alkenes and conjugated systems. There are two types of hydrogens in alkenes. Hydrogens directly attached to the double bond are known as vinylic hydrogens or vinyl hydrogens, whereas those located on the carbon atom attached to the double bond are called as allylic hydrogens. Each type of hydrogen resonates in a particular chemical shift. Now, the chemical shift values for vinylic hydrogens, that is double bond CH, are in the range of 4.2 to 6.5 ppm, whereas for allylic hydrogens, that is C double bond C single bond CH, is 1.6 to 2.6 ppm. Now students, both types of hydrogens are de-shielded due to the anisotropic effect of the pi electron cloud of the C double bond C. However, the effect is smaller for allylic hydrogens. As you can see, they are more upfield than the vinylic hydrogens because they are at a greater distance from the double bond as compared to vinylic hydrogens. If the system is conjugated, let us say of the type C double bond C, single bond C, double bond CH, the chemical shift is further moved to a more downfield region. Now in this figure, it shows the NMR spectrum, the proton spectrum of 2-methyl-1-pentene. Students, you should note here that the vinyl hydrogens demarcated as He, they appear at 4.7 ppm and the allylic methyl group appears at 1.7 ppm and allylic methylene groups appear at 1.9 ppm. You can see the various protons are marked and you can see their peaks in this figure. There may be 3 different types of spin-spin interactions in alkenes. The splitting patterns of both vinylic and allylic hydrogens is quite complex. The hydrogen atoms attached to a double bond are rarely equivalent and hence they couple to each other, forming a complex coupling system. Further complications may arise due to the allylic coupling. When allylic hydrogens are present in an alkene, they also show long range allylic coupling with hydrogens located on the far double bond carbon as well as the usual splitting due to the hydrogen on the adjacent carbon atom. Now you can see various types of conformations and their coupling constants. The J values are given here. Now for cis, the J3 value will be 6 to 15 Hertz. For trans, the J3 value will be 11 to 18 Hertz. For terminal methylene groups, that is for geminal protons, the J2 value will be 0 to 5 Hertz, and for the 4J value of trans alkenes, that is conjugated alkenes, will be 0 to 3 Hertz, and for cis ones it will be 0 to 3 Hertz, again the 4J values. Now let us come on to the discussion of aromatic compounds, students. In general, aromatic compounds have 2 types of hydrogens. One type of hydrogens which are directly attached to the benzene ring and the other types are benzylic hydrogens which are attached to the carbon atom attached to the benzene ring. Hydrogens attached to the benzene ring have larger chemical shift value, usually in the range of 6.5 to 8 ppm. The hydrogens on an aromatic ring are highly de-shielded than those attached to a normal double bond due to the large anisotropic effect generated by the circulation of the pi electrons of the benzene ring. Now, benzylic hydrogens are also de-shielded by the anisotropic effect of the pi system, but the effect is smaller due to more distance from the ring. Benzylic hydrogens appear in the range of 2.3 to 2.7 ppm. If the benzene ring is substituted with electron withdrawing groups such as nitro, chemical shift of the ring hydrogens is shifted to downfield region, that is towards high chemical shift values. These groups de-shield the attached hydrogens by withdrawing electron density from the ring through resonance interaction. On the other hand, students, the electron donating groups like methoxy etc. increase the shielding of ring hydrogens, causing them to shift towards the upfield region, that is towards the right hand of the NMR spectrum. In aromatic rings, coupling usually occurs beyond the adjacent carbon atoms also, that is for more than 3 bonds. The ring hydrogens, which are chemically as well as magnetically non-equivalent, interact with one another to produce a spin-spin splitting pattern. The extent of interaction depends on the distance that is between them. For orthohydrogen students, the J3 coupling values are between 7 to 10 Hertz and they couple more strongly than meta-hydrogens, for which 4J values are 1 to 3 Hertz, which in turn couple more strongly than para-hydrogens because there are 5 carbons involved. So, the 5J values are 0 to 1 Hertz. Now students, we can determine the substitution pattern of the ring from these splitting patterns and the magnitudes of the coupling constants. The para-substituted aromatic rings usually shows 2 doublets. The para-substitution NMR aromatic region pattern usually looks quite different than the patterns for both ortho and meta-substituted aromatic rings. Now students, the next functional group will be alkynes. The acetylenic hydrogens, that is hydrogens attached to the triple bond, have chemical shift values in the range of 1.7 to 2.7 ppm. The chemical shift value is moved towards upfield region than might be expected or shielded due to the anisotropic effect of the pi electronic system. The hydrogens on the carbon next to the triple bond are also affected, that means they are shielded by the pi system, and these protons resonate at approximately 1.6 to 2.6 ppm. The figure shows the proton NMR spectrum of 1 pentyne. The acetylenic hydrogen appears at 1.95 ppm and the allylic hydrogens, they appear at 2.2 ppm. Now you can see all the protons are marked and you can see their shielding and deshielding, and you can see their ppm values. Sometimes students, the acetylenic hydrogen may not show a sharp singlet due to the allylic coupling and may split into a triplet, but the coupling constant is quite small, that is J is equal to 2 to 3 Hertz. Now let us discuss about alkyl halides, next functional group. In alkyl halides, hydrogen atoms attached to the carbon to which the halogen is attached are deshielded due to the electronegativity of the halogen atom. The amount of deshielding increases as the electronegativity of the halogen increases. The chemical shift values range in RCH2F, RCH2Cl, RCH2Br, RCH2I, that means alkyl fluorides, chlorides, bromides and iodides are in the range of 4.2 to 4.8 ppm, 3.1 to 4.1 ppm, 2.7 to 4.1 ppm and 2 to 4 ppm respectively. Now compounds containing fluorine will show spin-spin splitting due to coupling between fluorine and the hydrogens on either the same or the adjacent carbon atom. That is, for CHF the coupling will be 50 Hertz and for CH-CF bond the coupling will be J3 will be 20 Hertz. Since the spin of fluorine is 1 by 2, then the n+1 rule can be used to predict the multiplicities of the attached hydrogens. The other halogens, that is iodine, chlorine, bromine, do not show any coupling. The proton NMR spectrum of 1-chlorobutane is shown in the figure that you can see. The hydrogen atoms nearest to chlorine resonate at the highest chemical shift value. Now you can see here all the protons are marked and you can see the upfield and downfield values of protons which are close to chlorine and which are farthest to chlorine. Now let us come to the next functional group of alcohols. The hydrogen of the hydroxyl group appears in the range of 0.5 to 5.5 ppm. The chemical shift of OH hydrogen is variable and its value depends on the concentration, solvent, temperature and the presence of water or of acidic or basic impurities. Students, the variability of OH signal is due to the OH proton exchange and the extent of hydrogen bonding in the solution. The peak may be broadened at its base by the same set of factors. Now, the OH hydrogen is usually not split by hydrogens on the adjacent carbon, that is CHOH, because rapid exchange decouples this interaction. Exchange is promoted by the increased temperature, small amount of acid impurities or the presence of water in the solution. In ultra pure alcohol samples, that is CHOH coupling is observed. A freshly purified and distilled alcohol may show this coupling. Now you can see how a coupling takes place, and if no coupling takes place because of exchange rate is fast. For detecting the protons exchangeable with D2O, either the spectrum is recorded in D2O or a few drops of D2O are added to the sample and shaken properly before recording the NMR spectrum. The proton is exchanged by D2O. If we can use this exchange reaction of an alcohol as a method, then we can identify the OH absorption clearly. For this, a small amount of D2O is added in the NMR tube containing the alcohol. After shaking for some time, the OH hydrogen is replaced by deuterium. Hence, the peak due to alcoholic hydrogen will disappear because deuterium absorbs at different field strength. Therefore, there will not be any coupling or splitting due to the proton which has been exchanged with deuterium. The hydrogen on the carbon adjacent to the hydroxyl group, that is CHOH, the CH hydrogen, appears in the range of 3.2 to 4 ppm due to de-shielding by the electronegative oxygen atom. If deuterium exchange has taken place, this hydrogen will also not show any coupling with the OH hydrogen, but may show coupling to other hydrogens which are adjacent to this carbon atom. If deuterium exchange is not been there, then the splitting pattern of this hydrogen may be complicated by different coupling of the proton with the hydroxyl group and the protons at the beta carbon. The phenolic OH is usually found in more de-shielded regions, that is between 4 to 7 ppm. The hydroxyl proton in enols appear in the range of 15 to 17 ppm. These chemical shift values are also variable and depend on the temperature, solvent and concentration of the solution. Now you can see in this figure the proton NMR spectrum of 2-methyl 1-propanol. Protons attached to the alpha carbon appeared in the most downfield region of 3.4 ppm. The hydroxyl group appeared as a triplet at 2.4 ppm. Here some coupling is observed for hydroxyl proton due to the hydrogens on the adjacent carbon. Now you can see clearly what I am trying to say from this figure. Now let us come to the discussion of the next functional group, which is ethers. In ethers, hydrogens on the alpha carbon are de-shielded due to the electronegativity of the oxygen atom. These hydrogens appear in the range of 3.2 to 3.8 ppm. Methoxy group can easily be identified as the methyl hydrogens of this will appear as a strong singlet. Epoxides are cyclic ethers, and in epoxides the de-shielding is not as strong as in alkyl ethers due to the ring strain. Now students, this factor has been very nicely discussed and discussed in detail in the previous modules. The methylene hydrogens in the ring appear at in the range of 2.4 to 3.5 ppm. Now this figure shows the proton NMR spectrum of butyl methyl ether. The absorption of the methyl and methylene hydrogens next to the oxygen is both seen at around 3.4 ppm. The methoxy peak is observed as a sharp singlet. The methylene hydrogens are split into a triplet by the hydrogens on the adjacent carbon in the alkyl chain. Let us now consider the next functional group, that is the amines. The amine protons appear as a broad peak, but not as broad as in carboxylic acid proton peak, in the range of about 0.5 to 4 ppm, and the range is extended in aromatic amines. The NH chemical shift is variable and is affected again like OH coupling peak by temperature, acidity, amount of hydrogen bonding and the solvent. Moreover, the NH protons show often broad and weak signals and rarely show coupling to the hydrogens on the adjacent carbon atom. This condition can be caused by chemical exchange of the NH proton or due to quadruple broadening. The amino hydrogens will exchange with D2O, causing the peak to disappear, as you can see in the reaction that is shown here. The NH peaks are strong in aromatic amines, where delocalization of the lone pair of electrons on the nitrogen appears to strengthen the NH bond by changing the hybridization. The hydrogens at the alpha carbon are slightly de-shielded by the presence of the electronegative nitrogen atom, and they appear in the range of 2.2 to 2.9 ppm. In aromatic amines, the alpha hydrogen is de-shielded due to anisotropy of the ring and also due to the resonance that decreases the electron density on nitrogen atom and changes its hybridization. Now, you can see that the figure which is shown here is telling you about the proton NMR spectrum of propyl amine. The NH proton appears as weak and broad singlet at 1.8 ppm. Note students that the NH proton does not show any coupling with the hydrogens on the adjacent carbon atom. Students, let us now move to the next functional group, which is the nitriles. In nitriles, hydrogens on the alpha carbon, that is CH-CN, the hydrogens belonging to the CH, are slightly de-shielded by the anisotropic effect of the pi electrons in the cyno group. These protons appear in the range of 2.1 to 3 ppm. Now let us consider nitroalkanes as next functional group. In nitroalkanes, the hydrogens which are attached to the carbon atom next to the nitro group are highly de-shielded and appear in the range of 4.1 to 4.3 ppm. The de-shielding effect of nitro group is due to the electronegativity of the attached hydrogen and the positive formal charge assigned to the nitrogen atom. Now students, let us consider aldehydes, that is the carbonyl compounds. The aldehydic proton, that is the CHO, appears in the range of 9 to 10 ppm, that is very downfield. The high value of chemical shift of this hydrogen is due to the anisotropic effect of carbonyl group, that is the C double bond O group. The peak in this region is highly particular for aldehydic protons because no other type of hydrogen appears in this region. Hydrogens attached to the alpha carbon, that is at RCH, CHO, are also de-shielded due to the anisotropy by carbonyl group, but the effect is obviously smaller because of the larger distance from the carbonyl group. These hydrogens appear in the range of 2.1 to 2.4 ppm. The aldehyde hydrogen, that is the CHO, couples weakly and the J3 value is 3 Hz with the hydrogens present on the alpha carbon atom. Thus, we can determine the number of hydrogen atoms at the alpha carbon just by looking at the multiplicity of the CHO proton. Now students, the signal due to the hydrogens on the alpha carbon are split by the aldehydic hydrogen and the splitting value is 3 Hz, as well as by the hydrogens on the next adjacent carbon in the alkyl chain, and for that the coupling constant is 8 Hz. All the carbonyl functional groups such as enones, aldehydes, esters, amides and carboxylic acids have this type of alpha hydrogens, that is CH-CO. Hence, they will all give NMR peaks in this region, that is of 2.1 to 2.4 ppm. Therefore, it is necessary to look for an aldehydic hydrogen peak at 9 to 10 ppm to confirm whether the compound is an aldehyde or not. Now, figure shown here to you shows the NMR proton spectrum of 2-methyl-butyraldehyde. The aldehydic proton appears at 9.6 ppm. Notice students that this peak is split into a fine doublet by the hydrogen on the carbon adjacent to the carbonyl group. The hydrogen next to the carbonyl group appears at 2.3 ppm because of larger distance from the electron withdrawing carbonyl group. Now, let us consider the next series of carbonyl compounds, that is ketones. In ketones, students, which have the general formula RCOR, the hydrogens on the alpha carbon atom, they appear in the range of 2.1 to 2.4 ppm. The other protons in the alkyl group will appear in the range of 0 to 2 ppm. The alpha hydrogens show coupling with hydrogens on the adjacent carbon atoms along as the alkyl chain. Methyl ketones can easily be distinguished as the sharp 3-proton singlet at approximately 2.1 ppm. All the carbonyl functional groups, students, that is ketones, aldehydes, esters, amides and carboxylic acids, will give rise to NMR absorptions in this same area. Hence, it is again very necessary to look for the absence of other compounds, that is aldehydes, hydroxyl groups, the amines, the OCH2R, that is the ethers, etc., to confirm whether the compound is a ketone or not. Now, have a look at this figure which is showing the proton spectrum of 3-methyl-2-pentanone. Notice that there is a sharp singlet at 2.1 ppm and which is a characteristic peak of methyl ketone. Now, you can easily by these factors distinguish between ketones and other functional group as well as other carbonyl containing functional groups. Let us now come to the next series of carbonyl containing functional groups, that is esters. There are two different types of hydrogens which are present in esters. Firstly, the hydrogens on the carbon attached to the oxygen, that is R C double bond O CH, are more de-shielded due to the electronegativity of the oxygen and they appear in the range of 3.5 to 4.8 ppm. The other types of hydrogens are alpha hydrogens, which can be denoted as RCH COOR, and they resonate in the range of 2.1 to 2.5 ppm. These protons are de-shielded by the anisotropy of the carbonyl functional group. Again, all type of carbonyl functional groups, they give rise to NMR absorptions in the range of 2.1 to 2.5 ppm due to alpha hydrogens. Therefore, for an ester group in a compound to be present, it should be identified by the NMR absorptions in the range of 3.4 to 4.8 ppm region. Both types of hydrogens can show coupling, normal vicinal coupling, that is, with the protons on the adjacent carbon atoms. Now, for this, understanding the spectrum of esters, let us have a look on the NMR proton spectrum of isobutyl acetate in the figure. A sharp singlet at 2.1 ppm is due to the presence of CH3CO group. The proton on the carbon attached to oxygen atom appears at 3.8 ppm as a doublet due to the coupling or the methine group of protons. The next functional group, students, that is the carboxylic acids. The carboxylic acid protons, that is the COH protons, appear in the range of 10 to 13 ppm as a broad singlet. Sometimes it is so broad that it is not even seen, with the exception of some special case of hydrogen in an enolic OH group that has strong internal hydrogen bonding, with no other type of hydrogen appears in this region. Thus, a peak in this region, that is 10 to 13 ppm region, is strong indication of a carboxylic acid functional group. Since the carboxylic acid proton has no neighboring proton, hence it is usually not split. In dilute and non-polar solvents like deuterated chloroform, carboxylic acids exist as stable hydrogen bonded dimers, and due to this, the carboxylic acid proton appears as a very broad singlet. In such conditions, the integral value cannot be used to identify the number of protons with accuracy, as it may cause an overestimation of the number of hydrogens in the molecule. The carboxylic proton is acidic, students, as you may know, because that is why it is known as acid, and may exchange with water and D2O. In D2O proton exchange, the COH group will convert into COOD by the exchange, and hence a peak near 12 ppm will disappear and a new peak will appear due to hydrogen of DOH. This exchange reaction is shown here to you. Carboxylic acids are often insoluble in CdCl3, and hence their spectra is used to determine in D2O, to which a small amount of sodium metal is added. This basic solution of NaOD D2O will remove the acidic proton, forming a soluble salt of the acid, and thus the COH absorption will disappear and a new peak at around 4.5 to 5 ppm will appear due to hydrogen of DOH. This exchange reaction is shown here as an equation, as you can see. Now, this figure is clearly showing you the proton NMR spectrum of pentanoic acid. The OH proton of carboxylic group appears at 12 ppm as a broad singlet near 12 ppm. Notice that this peak is not obtained as a broad singlet. The methylene hydrogens next to carboxylic acid group appear as a triplet at 2.1 ppm. This is the most downfield CH2 signal because it is closest to the electron withdrawing carboxylic group. Now, let us come to the discussion of the next and the final functional group, that is amides, in this module. Amides have three different types of hydrogens, that is those attached to nitrogen, that is RCONH, the hydrogens attached to alpha carbon, that is CHCONH, and the hydrogens which are attached to a carbon which is also attached to nitrogen atom, that can be represented as RCONCH. The chemical shift values for the protons attached to nitrogen are in the range of 5 to 9 ppm. The alpha hydrogens absorb in the same range, that is 2.1 to 2.5 ppm, as other acyl CH3CO hydrogens. They are slightly de-shielded by the carbonyl group. Hydrogens on the carbon attached to the nitrogen atom are slightly de-shielded, that is they fall in the region of 2.2 to 2.9 ppm due to the electronegativity of the nitrogen atom. It is important here to note that the proton or group of protons which is attached to the amide nitrogen often exhibits different chemical shifts. For example, the proton NMR spectrum of dimethyl formamide, also known as DMF, shows two distinct methyl peaks. In general, one can expect the two identical groups attached to nitrogen to be chemically equivalent because of free rotation of the CN bond. However, the rotation is restricted due to some extent because of the some double bond character between carbon and nitrogen in the amide bond. The double bond character arises due to the resonance between the unshared pair of electrons on nitrogen and the carbonyl group. You can see the exchange here, the partial double bond character in amide bond in this equation. Thus, if free rotation is slowed down, the hydrogens or group of hydrogens attached to nitrogen in an amide bond are non-equivalent and two different types of absorption peaks will be observed, one for each hydrogen. Nitrogen atoms also have a quadruple moment and its magnitude depends on the particular molecular environment. If the nitrogen atom has a large quadruple moment, the attached hydrogens will show broad peak with reduced intensity. Now, this figure here shows you the proton NMR spectrum of butyramide. Notice, students, that the two NH2 protons appear at different chemical shifts of about 6.6 and 7.2 ppm. This occurs due to restricted rotation about the CN bond. the methylene hydrogens next to CO group appear at 2.1 ppm. Let us summarize this module. In an alkyl group, methyl hydrogens are most shielded, followed by methylene and then methine protons. The chemical shift values for vinylic hydrogens are in the range of 4.5 to 6.5 ppm, whereas for allylic hydrogens it is 1.6 to 2.6 ppm. Both type of hydrogens are de-shielded due to the anisotropic effect of the pi electrons of the C double bond C, that is the double bond. Hydrogens attached to the benzene ring have a larger chemical shift value, usually in the range of 6.5 to 8 ppm. This unusual value of the chemical shift of aromatic hydrogens is due to the large anisotropic effect generated by the circulation of pi electrons. The acetylenic hydrogens are shielded due to again the anisotropic effect of the pi electron system, and hence it has a chemical shift value which ranges from 1.7 to 2.7 ppm. The aldehydic proton, the CHO proton that is, appears in the range of 9 to 10 ppm. The high value of chemical shift of this hydrogen is again due to the anisotropic effect of the pi electron of the carbonyl group. The chemical shift of the protons attached to nitrogen, oxygen, sulfur, etc. is variable depending on the concentration, solvent, temperature and the presence of water or of acidic or basic impurities. In general, the signal of these protons is obtained as a broad signal and it does not split by any other proton on the adjacent positions except only in some special cases.